We've talked about electron configurations, and so now we're going to start looking at electron configurations as atoms change as they react. So one of the easiest things to look at is what happens when we become ions. So again, one thing to remember is that things change to become more stable. If something's very unstable, it will change very easily. And the more stable it is, the more resistant it will be to change. So things will change until they settle into something that is stable. Remember that noble gases are very resistant to change. They don't form ions, and they very rarely form compounds. So the electron configuration for noble gases we say is ns2np6, where n is the row number. Sometimes we just simply say s2p6. The one exception, of course, is helium. Helium just has an electron configuration of 1s2. So let's look at what happens. So remember that all of our data is coming from experimental experiments. There's theories, but theories really don't mean anything in chemistry unless we actually have experimental data to back it up. So let's look at sodium. Sodium, as you know, is on the third row in the first column. So its electron configuration is neon, 3s1. The Z effective is not very high, right? The valence electrons are the third energy level from the nucleus. There's 10 electrons worth of shielding. So it's likely to lose its valence electrons, really not likely to gain its electrons. So when it loses the electron, it loses its 3s electron. And that makes sense because it's the most loosely held. It has the most shielding, it's farthest away. And it's on the outside, right? It's easier to grab things that are on the outside. And when it does so, the electron configuration of the Na+1 ion is helium, 2s2, 2p6. Notice we don't say neon. I don't just take this 3s1 electron and leave neon. I rewrite it as helium, 2s2, 2p6. And that's to remind us that now its valence electrons are on the second energy level with the shielding of helium. So the electron configuration, as you'll notice, is isoelectronic to the noble gas neon. So even though we don't write it as neon, we understand that it's isoelectronic to, meaning it has the same electron configuration as the noble gas. Well, we know that sodium plus 1 forms very readily. What about sodium plus 2? In order for sodium plus 2 to happen, I'd have to lose the second electron from the second energy level. Now notice that I now have the shielding of helium, not the shielding of neon. And that's 2 electrons. That's 1/5 of the original shielding. So there's less repulsive force. The valence electrons are now on the second energy level, not the third one. So the Z effective becomes very high. In fact, incredibly high, because sodium plus 1 is now isoelectronic to neon, but, so right, it has the same shielding and same valence electrons, but it's almost as if it's right here where it has one more proton than neon. And we know that the trend of Z effective increases as I go across from left to right across the periodic table. So if neon doesn't lose an electron, you know that sodium plus 1 is definitely not going to lose an electron. Okay. So remember that metals have a low Z effective, so they lose valence electrons to become cations, and they stop losing electrons when the electron configuration is stable. So we can predict what electrons, what ions, what the charge is going to be that metals are going to form. So let's look at aluminum, right? So aluminum, its electron configuration is neon, 3s2, 3p1. It's a metal. It's on the left side of the Zental boundary, so it's going to lose its electrons. And to lose electrons to become isoelectronic, it will lose 3 electrons, and it will gain the electron configuration of helium, 2s2, 2p6. And stop. In fact, it doesn't go beyond that. Barium. Barium is way down here, and its electron configuration is xenon, 6s2. Incredibly weak. And when it loses its 6s2 electrons, it becomes krypton 5s2, 4d10, 5p6. And you may say, well, those d orbital electrons, what are we going to do? They're not the highest energy level. You concentrate on the highest energy level, and as long as the highest energy level that is occupied has an S2p6 electron configuration, it's stable. So barium will stop at a +2 ion. And it won't even be a +1 ion, nor will you see aluminum as a +2 or a +1 ion, because remember that first rule is that things will continue to change until they've actually reached something that is much more stable. All right, so what about transition metals? So because the 3d or any d orbital electrons have a higher potential energy than the ns2np6, that's why they fill in later, the s2 orbital, they can be lost if there's a strong enough force pulling it off. So not the np6. So you always lose your valence electrons first because they're further out. So if I'm looking at vanadium, vanadium's right here, it has an electron configuration of argon 4s2 3d3. Vanadium will form a +1 ion, not happily, but it will, and it has an electron configuration of argon 3d3. It will usually lose another electron, and so the most stable conformation usually is V+2 ion, and it's argon 3d3. Remember, the d orbital electrons aren't included in the electron configuration of a noble gas, S2p6, and so V+2 is, for the most part, isoelectronic to a noble gas. Under strong conditions, like there's a lot of atoms that have a very strong Z effective and can pull off more electrons, vanadium can be coaxed to pull off 3 more electrons, adopting either the V+3, the V+4, or the V+5 ion. So the V+3 ion has the electron configuration of argon 3d2, V+4 is argon 3d1, and the V+5 is neon 3s2 3p6. So it's not until the +5 stage that it becomes truly isoelectronic to a noble gas, but you have to remember that anytime I have a cation, as I become more positively charged, it becomes harder and harder to pull off those electrons. So these 3 ions, the V+3, +4, and +5, really only occur when it's bonding with very strong Z effective elements such as nitrogen, oxygen, fluorine, or chlorine. So what about nonmetals? So remember that nonmetals have a high Z effective, which means they're going to tend to gain electrons to become anions, and again, they'll stop gaining once they have achieved a stable electron configuration. So let's look at nitrogen. Nitrogen is right here. Its electron configuration is helium 2s2 2p3. So it has a shielding of 2 electrons. Its valence electrons are only in the second energy level, so it has a very high Z effective. It will grab 3 electrons to attain the electron configuration of helium 2s2 2p6. So it's important to remember that even though it's at a stable electron configuration and it will stop, it will not continue to gain electrons. So the N-4 ion is impossible. Its electron configuration, if it happened, would be Ne3s1. Now, Ne3s1 means that it has a huge shielding. You know that sodium has a low Z effective, and it loses its valence electron, its 3s electron. Nitrogen -4 is, its valence electron is just as far away and has just as much shielding, but the nitrogen has 4 fewer protons than sodium, so it's even more weak than the sodium atom. Sodium becomes +1 very easily. You know that N-4 is not going to happen, right? You've increased the shielding by 5, and the energy level has gone up. So when we're talking about Z effective, also realize that N-3 has a lower Z effective than nitrogen. It's holding on to more electrons with fewer protons. So nitrogen only forms the -3 charge. What about other elements? I got bromine. Bromine is one of the dwindling number of nonmetals lower down on the periodic table. Remember, we talked about how you have fewer and fewer metals, nonmetals, and the nonmetals are always to the right. The reason why we have fewer and fewer nonmetals as we go down the periodic table is because the shielding and distance increase. So the Z effective needed to be a nonmetal becomes much, much harder and harder to attain. So bromine is a nonmetal. Its electron configuration is argon 4s2 3d10 4p5. It will form the bromine -1 ion, which becomes argon 4s2 3d10 4p6. You can see the stable electron configuration there. All right, so what do we do about something like polonium? Polonium has an electron configuration of xenon 6s2 4f14 5d10 6p4. At first glance, it would seem like, oh wow, I just have to gain 2 electrons to become radon. So if I did that, I would gain 2 electrons and I would attain, hey, 6s2 6p6 noble gas configuration. We love a noble gas configuration. And yet, we have to remember this thing right here. This thing is the Zintel boundary, and the Zintel boundary is experimentally derived, and it says that anything that is to the left of the Zintel boundary acts like a metal. And the key characteristic of metals is that they have a low Z effective and lose electrons. They can't gain electrons. So in fact, this is not what happens. What happens is that polonium loses 4 electrons, boom, 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 to become xenon 6s2 4f14 5d10. Why? Because the Zintel boundary cannot be overridden. The Z effective of polonium is too weak in order to gain, even though it seems like just a few electrons, in order to achieve that stable electron configuration. So instead it loses the +4 electrons in order to get to the next best thing, which is a D10 electron configuration. So remember that D10 is what we call an island of stability. So from this, we can figure out the ions that are most likely to form. If you're a metal, you're most likely to lose, you are going to lose electrons, and you're going to lose electrons to get to the next island of stability. So oftentimes it's an s2p6 electron configuration. For these ones that are post-transition metals, it will often get to just the D10. If you are a nonmetal, to the right of the Zintel boundary, you will gain electrons, and the number of electrons that you gain will be however many it takes to attain a noble gas electron configuration. This is also why the electron configuration and the ion that it forms of nonmetals is much more fixed than it is when we're talking about metals, because of those d orbital electrons. Nonmetals don't have to worry about because they're only going up, whereas the metals have to worry about that because they're losing electrons, and they may stop at islands of stability that aren't the s2p6.